This contribution, entitled Resonant Modal Couplings for Development of Fiber Loops Refractometers, contains the result I obtained during my research stay in the Laboratory of Fiber Optics. Here we present a robust refractive index sensing device easily fabricated with a loop of optical fiber, with a detailed characterization including the dependence of the coupling's resonant wavelength with the curvature, as well as the effect of temperature and the transient behavior. The operation principle of this sensing device is given by the bending of a single-mode strip fiber that produces a perturbation in the refractive index profile of the fiber due to both geometric and strain optic effects, and thus a transfer of power from the core mode into the cladding modes occurs at wavelengths that meet the phase matching condition. In the transmission spectra, this coupling phenomenon is evidenced by a series of attenuation notches centered at the corresponding resonant wavelengths. When cladding modes are excited, the evanescent wave senses variation in the external refractive index through changes in the modal index of these higher-order modes. Taking advantage of this interaction with the exterior, it is thus possible to construct a refractometer by monitoring the wavelength shift undergone by the transmission notches. The loops were fabricated by bending peeled single-mode standard telecommunication fiber around metallic cylinders and attaching them with commercial glue. The length of polymer coating removed was half the perimeter of each cylinder and was done in an acetone bath to avoid damaging the silica surface. The different diameters of the cylinder tested yielded curvatures in the range of 0.14 to 0.20 millimeters to the -1. The experimental setup employed consisted of a light-emitting diode and an optical spectrum analyzer of 20 picometers resolution. The addition of a polarizer and polarization controller to this setup was considered, but preliminary results proved it unnecessary. The transmission spectra of the aforementioned set of fiber loops were registered in the range between 1400 and 1700 nanometers. The resonant wavelength of a particular coupling was noted for the different curvatures in order to search for a pattern. This graph here shows the obtained value for the resonant wavelength of the loops when surrounded by air and also by water. The resulting behavior is linear in this narrow range of cylinder diameters. An important aspect to highlight from this graph is that the trend is preserved when the loop is immersed in different media, as both sets of points have a linear trend with a slope of approximately 2030 nanometers by millimeters. So there is no need to recalibrate the sensor when measuring in air or in aqueous solution. To assess the effect of temperature on the optical response of the resonant notch, a thermal chamber with a range from -10 to 80 degrees Celsius was employed. The transmission spectra were recorded before activating the thermal chambers, that is, at room temperature, and afterwards every 2 degrees centigrade in the previously mentioned interval. It is important to state that the temperature change does not only affect the diameter of the loop, but also the stress applied to the fiber as the metal cylinder dilates. Using a loop of 0.17 millimeters of curvature and a notch with resonant wavelength centered around 1495.36 nanometer at room temperature, this notch was monitored as a temperature change. From the resulting plot, a monotonically decreasing trend can be observed. The total wavelength shift in this wide temperature range studied is below 2 nanometers, that is significantly inferior to the 3 dB bandwidth of 19.7 nanometers that these notches have. Considering a characterization under normal conditions, we can conclude that the variations in the resonant wavelengths will be less than 0.2 nanometers for a 10-degree variation, that is, a temperature change throughout a day. Taking into consideration the redshift evidence when the loop was introduced in water, we can state the sensing performance of the devices as refractometers. Particularly, we studied in detail two loops of 0.17 and 0.19 millimeters of curvature, as both presented several resonant notches in the wavelength range studied. Here we present the behavior of three resonant notches of the aforementioned loops, which we named 1, 2, and 3 for simplicity. This plot here was constructed by registering the notches shift to longer wavelength as the external refractive index increased by the addition of ethanol to water. The slope of the data represents the sensitivity of each notch of the device, and the limit of detection is calculated by dividing the resolution with the obtained sensitivity. The resonant wavelength of one attenuation notch for both loops was monitored through time as the loop was immersed in and out of ethanol water solutions at 0, 20, 40, and 60% volume in volume. When the loop was retrieved, it was dried with nitrogen gas to evaporate the leftover liquid in the device and left in air once again. Here we present the curve obtained for the 0.19 mm loop. The results show the red shift of the resonant notch of the loop during this process consistent with the sensitivity previously obtained. It can be observed that the resonant notch returned to the original position with a maximum deviation of 0.081%. To conclude, the presented device has the great advantages of easy manufacturing and its resonant nature, with the ability to monitor wavelength shifts in a broad refractive index range without certainty due to the traceability of the different notches present in the transmission spectra. However, for its optimum performance, one needs to add a reference element to disregard the wavelength shift due to variations of stress and temperature. Here, we calibrated a combination of both effects to estimate and provide the required information to select such a reference element. Sensitivities obtained for the 0.17 mm to the -1 loop are around 300 nanometers per refractive index unit, and thus comparable with the results present in the literature for wavelength shift-based sensor in the same refractive index range. Thanks to its overall performance, these devices have good prospects to develop biosensing application as well as material deposition sensing.